There's an extremely peculiar object currently passing through our solar system, right now, moving near our star. We don't have absolute certainty about its exact nature or what it's doing out there. In fact, at this very moment, we can no longer observe it directly. However, we have been meticulously monitoring this object for several months. We've assigned a specific name, 3I/Atlas, and given it classification, interstellar comet. There's a considerable amount of data we've gathered about this new visitor that has entered our cosmic neighborhood. In just 4 months, the scientific community has published nearly 100 research papers dedicated to 3I/Atlas, not to mention the vast amount of additional information circulating outside official records. Some of this information might sound absolutely far-fetched. That's why today we're going to filter out all that informational noise and get to the bottom of what you really need to know about 3I/Atlas. If you find this content interesting, don't forget to subscribe to the channel and leave a comment telling us what you think about this fascinating interstellar object. Let's talk about the journey this interstellar traveler has been taking. Right now, 3I/Atlas is making its closest approach to the Sun, a phase we call perihelion. The peak of this approach occurs on October 29th, when the object passes about 210 million kilometers from our star. In space terms, we usually use a larger unit of measurement, the astronomical unit, or AU. 1 AU represents the average distance between Earth and the Sun, helping us bring a sense of familiar scale to the vastness of the solar system. So, the perihelion of 3I/Atlas occurs at a distance of 1.4 astronomical units from the Sun, meaning it doesn't actually get that close. It's somewhere just inside Mars's orbit. But this will be the moment of maximum activity for 3I/Atlas, the moment it reaches its highest temperature, causing large amounts of material from the object's surface to be expelled into space. Now, this is completely normal for a comet. We call this process sublimation, when a solid turns directly into gas because there's no liquid phase in the vacuum of space. Sublimation is what gives a comet its distinctive appearance, with a diffuse halo and a long tail. The halo is made of gas and dust being expelled from the object's solid surface, technically known as a coma. The tail is created by the solar wind, the stream of radiation constantly flowing from the sun's surface. This wind blows away the lighter particles of dust and gas from the coma, pushing them outward away from the comet. It's a spectacular piece of cosmic ballet. Unfortunately, we can't actually see this happening with 3I/Atlas as it moves through its peak exposure to the sun, because we're on the wrong side. Call it fate or something else. Our view of the perihelion is completely blocked by the sun's glare. Alright, we know where 3I/Atlas is right now, and we have a fairly good idea of what it's doing. So, while we wait for it to reappear on the other side, that gives us a chance to investigate how it got here in the first place. And this is a deeply fascinating story worth telling in detail. We've been tracking 3I/Atlas since July 2025. It was officially detected by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, which is actually a network of telescopes located around the world in places like Hawaii, Chile, and South Africa. These telescopes spend their nights watching the sky, looking for moving objects. And that's exactly what they spotted on the night of July 1st. Just another moving object. So they classified it as a new asteroid and were ready to move on. But then they noticed something strange about this one. It was moving too fast. Everything in space is constantly moving. Every object in the solar system orbits the sun because we're all trapped by its gravity. The fact that we're moving is what keeps us from falling into its gravitational well. The closer you get to the sun, the faster you have to move to stay afloat. But if you start moving fast enough, you actually begin to climb out of that well. And if you reach a certain speed, you break completely free of the sun's gravity and can travel into interstellar space, the empty void between the stars. When astronomers measured the speed of this new asteroid, they were completely stunned. This was the fastest moving object ever detected in our solar system. Let's set some scale so you can understand just how extraordinary this is. The planet Earth orbits the Sun at a speed of 30 kilometers per second. That's us, moving quite fast and fairly close to the Sun. But there are planets even closer. Take Mercury. At 0.4 astronomical units from the Sun's surface, it's scorching hot there, and to avoid falling into the Sun's gravity well, Mercury must orbit at about 48 kilometers per second. The newly discovered object, 3I/Atlas, was moving at 58 kilometers per second, and at that time it was still very far away, just inside Jupiter's orbit, about $4.50 from the Sun. At that speed, it was clear that this object would swing past the Sun and simply keep going. We call this a hyperbolic trajectory, which means this thing came from the void, from interstellar space, and that's exactly where it headed back after completing its grand passage through our solar system. This is the moment when the name 3I/Atlas emerged, the third interstellar object, meaning there were two before it. You probably know this one, Oumuamua, the first interstellar visitor ever identified. And it was quite strange, though strange in a completely different way than 3I/Atlas, and we'll dive into that very soon. But there's also a second interstellar object, the often overlooked middle child, 2I/Borisov, which actually wasn't that strange at all, apart from being interstellar. It basically behaved like a normal comet. So, if anything, it was strangely not strange. There are three major differences between 3I/Atlas and its interstellar siblings. One is size. It's literally much larger. Oumuamua measured up to 400 meters wide, Borisov up to 1 kilometer, but 3I/Atlas could be as large as 5.6 kilometers across. 2 is speed. Atlas travels at roughly twice the velocity of Oumuamua and Borisov. And 3 is the direction from which the object came, and this one is the truly bizarre part. Oumuamua came from above, from a northern sky, which is a general direction in which the solar system itself is moving. All of us orbit the Sun, but the Sun itself is also orbiting the center of the Milky Way galaxy, dragging us along with it. So, as much as Oumuamua ran into us, we also ran into it. 2I/Borisov did almost the same thing, entering at a more diagonal angle, but still from roughly the same direction. Now, 3I/Atlas is not another head-on collision. This one is a side impact, entering at a lateral angle in an almost perfect alignment with all the planets. Our solar system is like a disk of material that formed around the Sun. Over time, all that matter kept colliding and forming into planets, moons, asteroids, and so on, but all stayed within a relatively flat, disk-like shape. We call that disk the plane of the ecliptic. There are only a few things that deviate slightly from that plane. The most recognizable example would be Pluto. Its orbit is tilted by 17 degrees, meaning sometimes it's slightly above the ecliptic plane, and sometimes below it. It's important to know that so we can appreciate how perfectly aligned 3I/Atlas actually is. The interstellar object is only 3 degrees off that ecliptic plane. It struck our solar system in near-perfect alignment with the disk. Space is three-dimensional, and this object could have come from any direction. So having something hit us almost perfectly from the side is an enormous coincidence. But that brings us to an even bigger question. Where did 3I/Atlas come from? Well, we know it came from the direction of the galactic core. So, if we look at the Milky Way from the usual top-down view, you're here, in this outer half of the galaxy, located on a spiral arm. When you look at the Milky Way across the night sky, that bright band is the next spiral arm over. Anyway, 3I/Atlas came from the direction of that bright central core. It's bright because it's packed with stars, far more densely than in our local region. But again, space is three-dimensional. So, to really understand where 3I/Atlas originated, we need to flip the galaxy to a side view. Just like our solar system, most of the material in the Milky Way is concentrated in a thin disk around the core. But also like our solar system, there are some things that hang out above and below that thin disk. In the galaxy, we call that region the thick disk. It's much less crowded in the thick disk, meaning there are far fewer massive collisions, supernova explosions, or black holes. So, objects in this region tend to remain undisturbed for extremely long periods of time. And that's where astronomers believe 3I/Atlas came from, this ancient region of space, which could make as old as 7.66 billion years, almost twice the age of our own planet. We'll probably never be able to trace the full journey of 3I/Atlas back to its exact point of origin, but astronomers have recently managed to rewind its path by more than 10 million years, identifying 93 stars the object would have encountered along the way. But what's deeply fascinating is that during those 10 million years, the closest it would come to any of those 93 stars was 0.3 light years. That's 63,000 astronomical units. And right now, 3I/Atlas is only $1.40 from our own sun. Let's talk a bit more about how 3I/Atlas approached the sun and what we learned about it along the way. Although 3I/Atlas was officially discovered on July 1st, it was actually first detected on May 7th, 2025. It appeared in images captured by the Transiting Exoplanet Survey satellite TESS, an observatory that orbits Earth and looks deep into the galaxy to identify new planets in other star systems. And for about a month, TESS happened to be looking directly in the direction of 3I/Atlas. This gave us a chance to track the object as it moved across Jupiter's orbit. The first thing astronomers wanted to measure was the brightness of the object and how it changed over time. That tells us what it's made of. We know that during the month 3I/Atlas was observed by TESS, it traveled roughly 1 astronomical unit closer to the sun. So, we expect it to get brighter over that time. Astronomers use a term called flux to describe the perceived brightness of an object in space. Here's an example how this works. Think about how bright the sun looks from your location at noon on a clear day. Now imagine being transported to the surface of Mercury. That same sun would suddenly appear much brighter, bright enough to vaporize you. The sun's actual brightness hasn't changed, only your perception of it. That's flux. So, astronomers hypothesized that the flux of 3I/Atlas would increase by a factor of 1.5 between May and June. But the test data showed that the flux actually increased by a factor of 5, a massive surge in the amount of light the object was reflecting. And that's how we know this is an asteroid. It must be a comet, beginning to form its coma of gas and dust, the material responsible for reflecting all that excess light. Only, there are two strange things about this observation. One has to do with light polarization. Now, this is tricky to explain, so we'll simplify a lot here. When sunlight hits a cloud of gas and dust surrounding 3I/Atlas, it scatters in different directions. But the direction in which the light bounces isn't random. It tells us a lot about the material it's striking. If light scatters sideways, at a right angle or perpendicular, that's called positive polarization. If the light bounces straight back, in a parallel direction, that's called negative polarization. Most objects in space have mostly positive polarization, even interstellar ones. 2I/Borisov was positive, but 3I/Atlas is negative, and not just slightly. It has the most extreme negative polarization ever recorded for any object in space. That's pretty strange. And it's just one of many oddities about 3I/Atlas that tell us not all solar systems are the same. What we consider normal here might be unusual elsewhere, and what's normal in a different stellar system might seem strange to us. Then, the second surprising thing about the coma of 3I/Atlas was the fact that it even existed at all. Remember, we're talking about the period between May and June, and 3I/Atlas was still very far away, beyond Jupiter's orbit, more than 5 astronomical units from the Sun. It's cold out there, extremely cold. So cold that we normally don't detect comets at 5 AU, because they usually haven't started forming their coma yet. They're still frozen solid. Typically, sublimation doesn't begin until somewhere between 3 and 4 AU, because the comets in our solar system are usually made of water ice, which requires a lot of energy to melt. But as we kept observing 3I/Atlas and began pointing our most powerful telescopes directly at it, we discovered that its coma was actually dominated by CO2 gas. There was some water vapor, but a ratio of CO2 to H2O was much higher, about 8 to 1. That's basically the inverse of what we're used to finding in comets. If you've ever seen dry ice, commonly used to create smoky effects in live performances, that's frozen CO2. It has to be created and stored at incredibly low temperatures, and as soon as it's removed from deep freeze, it begins to sublimate instantly, creating that signature fog of gas. That's exactly what 3I/Atlas was doing out there in space, and that's why its coma formed so early, because CO2 ice sublimates at a much lower temperature than water ice. We've continued observing 3I/Atlas as it approaches the Sun and have seen that ratio of CO2 to water start to change. By late September, as it passed through Mars's orbit at just over $1.50, the object had begun releasing a massive amount of water vapor, roughly the equivalent of a fire hose running at full power. That's actually more water than we'd expect even from a normal comet at that distance. We've never seen so much water vapor appear so suddenly. The same could be said for the metal content in the coma of 3I/Atlas. When it was observed during the summer, astronomers detected a small amount of nickel in the surrounding cloud, but no iron. There are a couple of things to note here. First, nickel and iron are very common in the universe because they form the cores of dying stars. Those stars then go supernova, ejecting these metals into surrounding space, where they're later drawn into new stars forming their own planetary disks, and the cycle repeats. Since nickel and iron come from the same source, they're usually found together in planets, moons, asteroids, and comets. So when we see lots of nickel but no iron, we have to ask, where did the iron go? What process separated them? And second, it's strange to see any metal sublimating from 3I/Atlas at the distance where this observation was made. It was still far beyond Mars, in the asteroid belt region, which is still very cold, and sublimation is driven by heat. Now, when it comes to CO2, we know it doesn't need much heat to melt. But when we're talking about metal, something else must be happening. It's likely that the massive release of CO2 gas was dragging nickel atoms along with it, but that still doesn't explain the lack of iron. Just like water vapor appeared suddenly in the coma of 3I/Atlas, iron eventually did too. By late September, astronomers had begun detecting iron for the first time in the coma, and very quickly, the nickel-to-iron ratio shifted to a more normal balance between the two. So, 3I/Atlas is becoming more normal over time, but it's getting there in a very strange way. Now, let's talk about the tails. This is another area where 3I/Atlas has behaved quite differently from your average comet. Mainly because the first time we saw a tail forming around 3I/Atlas, back in the summer, it was actually pointing in the wrong direction. The object initially formed a tail facing the sun. That's unusual, since a comet's tail is caused by the solar wind interacting with the coma, and the solar wind always blows away from the sun. So we expect the tail to flow in that direction. In this case, it didn't, which may be related to the early formation of the coma caused by the high CO2 concentration. Because the object began sublimating at such a large distance from the sun, the solar wind may simply not have been strong enough yet to push the gas and dust cloud outward. So what we saw instead was a cloud accumulating on the warm side of the object, the side facing the sun, before encountering a strong enough solar wind to form a conventional tail, which 3i/Atlas eventually did. By September, it had developed a short, fan-shaped tail pointing away from the sun, which is actually quite normal. Not all comets have long, streaking tails like the ones we're used to seeing in illustrations. Tail length varies depending on what the comet is made of and its distance from the sun. For example, Hale-Bopp is famous for its enormous tail when it was observed in 1997. But it was also much closer to the sun at the time, about $0.90, roughly half an AU closer than 3i/Atlas will ever get. So, of course, it experienced much more sublimation and solar wind activity, which shaped that long tail. Around this time, we actually got our closest possible observation of 3i/Atlas. But the view didn't come from Earth, it came from Mars. On October 3rd, the object passed just 19 cents from the red planet, the closest it will come to any planet in the solar system. And that's fortunate for us, because we have lots of cameras in and around Mars, meaning we were able to use them to photograph 3i/Atlas. Here's a photograph taken by the Perseverance rover from the Martian surface. This is how the object would have appeared in the night sky. It's not a great image. The rover's camera wasn't designed for this kind of observation. To capture that faint light, the camera had to take 30-second long exposures, and several of those images were stacked together, resulting in more of a streak than a defined object. Here's another image of 3i/Atlas taken by the European Space Agency's ExoMars orbiter, which remains in orbit around Mars. We can see the object a bit more clearly now, but there still isn't enough resolution to distinguish between the bright coma and the object's solid surface itself. To get that finer detail, we'd need a photo from NASA's Mars Reconnaissance Orbiter, which has the most powerful telescope in the Martian system. Unfortunately, at the time of making this video, that image hasn't been released, if it was even taken at all. Essentially, there's been a U.S. government shutdown and NASA personnel aren't working until certain political matters are resolved, which, unfortunately, might take some time. But time is something we do have right now, because the sun will continue blocking our view of 3i/Atlas until early December, when we'll finally be able to study the effects the sun had on the object. The closest we'll get will still be $1.10, and that happens on December 19th. By that point, 3i/Atlas will already be well on its way out of the solar system. But there's one final close encounter still to come. On March 16th, 2026, the object will fly 36 cents past Jupiter. While we don't have nearly as many cameras around Jupiter as we do around Mars, we do have one aboard a spacecraft called Juno, which has spent the past decade studying the gas giant and its moons. It'll have a chance to capture one final image of 3i/Atlas before it disappears forever. Now, at this distance, the object will be cooling down. It's going to be less active, but it may have been altered by its exposure to the sun, and that will add an extra layer of understanding to these interstellar objects. It's entirely possible that many of these strange features didn't even originate in the place where the object was formed. They could just be a collection of odd traits it picked up along the way. What makes this object so special isn't just its size or its speed, but the unique window it gives us into other solar systems. Every measurement we take, every anomaly we uncover, tells us a story about a place in the universe we will never be able to visit. This comet has traveled for millions of years through interstellar space, a journey so long it's almost impossible for the human mind to comprehend. Think about that for a moment. When 3i/Atlas began its journey, our own planet was a very different place. Human civilizations didn't exist yet. The dinosaurs had long since vanished. The world was populated by creatures we now know only from fossils. And throughout all that time, this object had been traveling silently through the void, unseen, unknown, until it finally crossed our path. The chemical composition of 3I/Atlas is also revealing fascinating secrets. That dominance of CO2 over water tells us something fundamental about the environment in which it formed. Comets in our solar system formed in a specific region, under certain temperatures, and with particular elemental abundances. The fact that 3I/Atlas has such a different composition suggests that it formed under very different conditions, perhaps around a cooler or hotter star than our Sun, or maybe in a region of its native solar system that was chemically distinct from our own Oort cloud. The extreme negative polarization we mentioned earlier is another intriguing mystery. This feature tells us something about the physical structure of the material in the comet's coma. The dust particles must have a very specific shape, size, or composition to produce this type of polarization. It's as if interstellar dust has fundamentally different optical properties from the dust in our own solar system. This could mean that the processes that created that dust, whether through collision, space weathering, or condensation in the original nebula, were very different from those that formed dust in our neighborhood. There's something deeply human about our fascination with objects like 3I/Atlas. They remind us that our solar system isn't an isolated place in the universe. We are constantly being visited by material from elsewhere, from other stars, other worlds. Each of these visitors carries information about places far beyond our reach, at least with today's technology. The trajectory of 3I/Atlas is also remarkable for its alignment with the ecliptic plane. Those 3 degrees of inclination are extraordinarily small when you consider the vast three-dimensional space it's traveling through. It's almost as if the object had been launched specifically to intercept our solar system in the most efficient way possible. Of course, that's just a coincidence, but it's a coincidence that makes us think about the nature of interstellar space. How many other objects like 3I/Atlas are out there drifting between the stars? How many have passed through our solar system unnoticed? Before 2017, when we discovered Oumuamua, we had no idea that these interstellar objects even existed. Now we know that the space between stars isn't empty. It's populated by these lonely travelers, each with its own story to tell. The velocity of 3I/Atlas is particularly interesting when compared to the escape velocities of various stellar systems. At 58 kilometers per second, this object must have received a significant boost at some point in its past. Perhaps it was ejected from its home system by a close encounter with a giant planet, similar to how Jupiter occasionally slings comets out of our own solar system. Or maybe it was accelerated by a close pass with another star, or even through a series of complex gravitational interactions. What's certain is that this object has experienced a complex dynamic history. It's not just a chunk of rock drifting quietly for billions of years. It has interacted with other bodies, felt powerful gravitational forces, and been shaped by those experiences in ways we are only beginning to understand. The fact that we can trace a trajectory back 10 million years is a testament to the power of mathematics and modern astronomy. We can calculate where this object has been, which stars it passed near, and how its path has been influenced by the gravitational forces of the galactic neighborhood. It's like reading a cosmic history book written in the language of orbital physics. The TESS observations were particularly valuable because they gave us a continuous observation period lasting an entire month. In astronomy, continuity is gold. Often, we can only observe objects intermittently, when weather conditions are favorable or when telescopes aren't booked for other projects. But with TESS, we had an uninterrupted view of 3I/Atlas for 30 consecutive days, allowing us to detect subtle changes that we might otherwise have missed. That 5-fold increase in light flux was a total surprise. Theoretical models simply didn't predict anything like it. Astronomers expected a modest increase, consistent with an object gradually approaching the sun and slowly heating up. But what they saw was a dramatic transformation, as if the object had suddenly awakened from a deep sleep. This early, Intense activity tells us that the models we use to understand comets, models built on decades of studying those from our own solar system, simply don't apply in the same way to interstellar visitors. And that makes sense when you think about it. Comets in our solar system formed about 4.5 billion years ago from the same disk of material that created the sun and planets. They've been orbiting in the same neighborhood ever since. We know their story because it's our shared story. But 3I/Atlas comes from a completely different place, with a completely different history, a product of conditions we can only imagine. The sudden appearance of water vapor in September adds another layer of complexity to this story. For months, the object had been releasing mostly CO2, and then suddenly, water began flowing like a fire hose. What caused this change? One possibility is that the object has a layered structure like a cosmic onion. The outermost layer could be rich in CO2, which sublimates easily even far from the sun. But beneath that could lie a deeper water ice, rich layer, protected from sublimation by the material above it. As the CO2 sublimates and escapes into space, it eventually exposes this underlying layer of water. And when that layer finally becomes exposed to solar radiation, it begins to sublimate rapidly, producing the massive release of water vapor that was observed. It's like peeling away the layers of an onion, revealing different chemical compositions as you move toward the core of the object. This idea of a layered structure isn't new in comet science, but the scale and dramatic nature of the changes we're seeing in 3I/Atlas are unprecedented. We've never seen a comet transition so quickly from a CO2-dominated composition to one dominated by water. This suggests that either the layering is very pronounced, with chemically distinct strata, or that some other, as yet unknown process is at work. The nickel and iron mystery is equally fascinating. These heavy metals shouldn't be sublimating at all at the temperatures 3I/Atlas experienced during the summer. Iron, in particular, has an extremely high sublimation point, far higher than CO2 or water. So, how did these metallic atoms end up in the comet's coma? One theory is that these metals aren't sublimating directly from the comet's surface. Instead, they're being mechanically dragged away by the massive outflow of CO2 gas. Imagine a river of gas streaming from the comet's surface, powerful enough to tear tiny metal particles loose and carry them into space, where they become part of the coma. It's similar to how a river on Earth can transport sediments and particles much heavier than the water itself. But that still doesn't explain why we saw nickel without iron at first. If both metals are being dragged away mechanically, why did one appear before the other? One possibility is that nickel was concentrated in a particular region of the surface that was exposed to sunlight first. As the comet rotated and new regions came into view, we may have reached a zone richer in iron, which is when we began to detect iron in the coma. Another, more intriguing possibility is that nickel and iron exist in different chemical forms within the comet. Perhaps nickel occurs as pure metallic grains that are easily dislodged by the gas flow, while iron is locked within more complex minerals that are harder to free. Only when sublimation intensified, as the comet drew closer to the sun, did these iron-bearing minerals finally begin to break down and release their contents. This kind of detective reasoning is what makes astronomy so exciting. We're trying to reconstruct the history and composition of an object millions of kilometers away using only light. Every photon we capture carries information, and our job is to decode that information to build a coherent picture of what's happening. The sunward-pointing tail that 3I/Atlas initially formed is another one of those fascinating details that defy our expectations. In most comets, the tail always points away from the sun because it's pushed by the solar wind. But in the early stages of 3I/Atlas's activity, when it was still far from the sun, the solar wind simply wasn't strong enough to push away the material that was sublimating. Instead, we saw the material accumulate on the sunward side of the comet, the warmer side. It's like when you open a door on a cold day and the warm air inside flows outward. But there's no wind. That warm air just lingers near the doorway instead of being blown away. Only when 3I/Atlas came close enough to the sun did the solar wind grow strong enough to sweep all that accumulated material away, forming a conventional tail that pointed away from the sun. This sequence of events gives us a window into the physical processes that shape comets. It's not just a matter of heat and cold, but the interaction between the outflowing gas and the solar wind, a dynamic balance that's constantly changing as the comet moves along its orbit. The images we obtained from Mars were an unexpected gift. Having multiple observation points in the solar system allows us to view objects from different angles and lighting conditions. The Perseverance rover wasn't designed to be a telescope, but it did an admirable job capturing what it could 3I/Atlas. Those long, stacked exposures represent the ingenuity of the scientists and engineers who found a way to repurpose existing tools for entirely new scientific goals. The ExoMars probe gave us a slightly better view from its orbital position. From there, the coma, that diffuse halo of gas and dust surrounding the comet's nucleus, was more visible. But even with that improved view, the nucleus itself, the solid rock or chunk of ice at the center, remains hidden within the bright coma. It's frustratingly elusive, this object that has traveled so far just to visit us. The possibility that the Mars Reconnaissance Orbiter may have captured an image with its powerful telescope is thrilling. If that image exists and is eventually released, it could reveal details we simply can't see from anywhere else. We might be able to discern structures within the coma, patterns in the dust distribution, perhaps even a glimpse of the nucleus's shape itself. But for now, we must wait. Patient is always in science, for political and logistical circumstances to align. The current period, when 3I/Atlas is hidden behind the sun from our point of view, is both a frustration and an opportunity. It's frustrating because we can't observe what's happening during perihelion, the moment of maximum activity. We're missing the main event. But it's also an opportunity because it gives us time to analyze all the data we've already gathered, refine our models, and make predictions about how the comet will look when it reappears. When 3I/Atlas emerges from the other side of the sun in December, it will have changed. It will have lost a significant amount of mass through sublimation. Its surface composition will likely be different, with some outer layers gone and new ones exposed. It may even be rotating at a different speed if the asymmetric release of gas acted like a small rocket, altering its spin. All of these things are observable, and each will tell us something new about this interstellar visitor. The encounter with Jupiter in March 2026 will be its final farewell. By then, 3I/Atlas will be cold again, its coma shrinking or perhaps disappearing entirely as the remaining ice becomes too cold to sublimate. The Juno spacecraft, if it's lucky with its timing and trajectory, might capture some final images of this traveler as it passes by. And then, 3I/Atlas will continue its journey into interstellar space, carry with it all the secrets we couldn't uncover. Think of all the questions that will remain unanswered. What is the exact shape of the nucleus? Is it spherical, elongated, irregular? Does it bear craters from ancient impacts? How deep are those layers of differing compositions? Are there complex organic compounds hidden within? Prebiotic molecules that could tell us something about the potential for life in other solar systems? These questions will haunt us because we know we'll probably never have the answers. 3I/Atlas will leave and never return. Unlike comets from our own solar system, which orbit the sun in predictable cycles and can be observed again and again, interstellar objects are one-time opportunities. We see them once, study them as best we can, and then they're gone forever. But that's what makes every observation precious. Every piece of data we collect is irreplaceable, and what we learn from 3I/Atlas will inform our understanding of the next interstellar visitor. because now we know there will be more. They are no longer theoretical rarities, but observational realities. The space between the stars is populated by these wanderers, and every so often, one passes close enough to our sun for us to catch a glimpse. Each new interstellar visitor is like receiving a message in a cosmic bottle, a sample from another place, another time, another set of conditions. And through the careful study of these messages, we're slowly building a broader understanding of the universe. We're learning that the diversity of worlds and objects is far greater than we ever imagined when we could only study our own solar system. 3i/Atlas has taught us that comets can have extreme negative polarization. It has taught us that CO2 can dominate over water in some environments. It has taught us that metals can appear in the coma in unexpected patterns, and that tails can point toward the sun before turning away. Each of these lessons expands our understanding of what's possible. And beyond the scientific details, 3i/Atlas reminds us of our connection to the wider cosmos. We are not isolated. We are not alone in the universe. We are part of a vibrant, dynamic galaxy where material flows between stars, where objects travel for eons through the void, where stories written in chemical compositions and orbital paths await our interpretation. So as we wait for 3i/Atlas to reappear in December, as we anticipate those final observations from Juno next year, let's take a moment to appreciate the incredible fortune of living in a time when we can detect and study interstellar visitors. Just a few decades ago, we didn't have the technology. Just a few years ago, we didn't even know they existed. And now, here we are, tracking 3i/Atlas through our solar system, deciphering its secrets one photon at a time. If you found this story as fascinating as we have, be sure to subscribe so you don't miss future updates on 3i/Atlas and other amazing astronomical discoveries. And leave a comment below telling us which aspect of this interstellar comet intrigued you most. Was it the extreme negative polarization? The CO2-dominated composition? The dizzying speed? Or perhaps the incredible coincidence of its alignment with the ecliptic plane? We'd love to hear your thoughts. For now, we can only speculate about what the future holds. Maybe in a few years, another interstellar visitor will cross our path, one even stranger than 3i/Atlas. Or perhaps we'll develop the technology to intercept one of these objects, to send a probe that can travel alongside it, studying it up close, maybe even landing on its surface. How amazing would it be to physically touch a fragment from another solar system, to bring samples back to Earth for detailed laboratory analysis? Those dreams may seem distant now, but the history of space exploration has taught us that today's impossibilities can become tomorrow's realities. And in the meantime, we'll keep watching the skies, searching for the next visitor, ready to ask the questions that will help us understand our place in this vast and wondrous universe.